Good morning. Thank you for joining us to this computing seminar that has been organized with the participation, well, actually with the active participation of our PH colleague, Vasilev. So we have the pleasure of having the visit today of Chaos Group, which is a Bulgarian company, if I understand it right. And we have with us the founder and CTO, who will start, Vladimir Koylazov, who will start presenting a little bit the activities of the group and give some sort of introduction as well to the speakers of this afternoon. So just for you to picture the event, we start this morning with a general presentation plus the specific technical part that Vladimir is going to present, or Vlado, no? Yes, Vlado as well. And then we have this afternoon at 2 o'clock, two small presentations of half an hour, around half an hour each, following to each other. So, I mean, if you come, you essentially will be another 1 hour something, yeah, this afternoon after lunch. We are recording it. I mean, you have accepted kindly that we have the 3 presentations recorded. So this means that we will be using the microphones as well for you. So I kindly ask you to use the microphone that you have closer to you in order to get your question recorded into the recording. Some other things is just if you have mobile phones with you, please put them in silent mode so we don't get disturbed. About the question style, I don't know how it is your preference.
We'll see how it goes.
Yes, we see how does it go. My proposal is if you have long questions or maybe comments to elaborate on what is being presented, better keep them to the end, and like this we don't interrupt the flow of the presentation. Otherwise, feel free, I guess. Yeah?
Yeah, it's okay.
Okay, so let's start now with the first presentation, and then I think that you will make some introduction of the speakers of this afternoon too, right?
Yes. Hello. First of all, I would like to thank Vasil for organizing, for inviting us here, and for giving us a tour of CERN, and for giving us a chance to present our work. I hope it's different than what people here are doing, but I hope that, and Vasil hopes that maybe it will be useful for you to know a little bit of how we do things, and maybe you can find some ideas that you can use. I am the CTO of Chaos Group. It's a company that we founded more than 10 years ago in 1997. What we do mostly is we have 2 main products. One is a rendering engine. It's called V-Ray, and it's used for basically you give it a 3D model. You define the lights and the materials in your 3D model, and it produces or at least attempts to produce a photoreal image of that 3D model by following the physics of of how light behaves in the real world as closely as possible. Here are some examples of things that people have been doing with our software. There's just some images that people have done for various projects. It's used also in many movies. If you have seen any movie in a theater this year, you've probably seen a little bit or more of V-Ray. And also, so making nice images is one thing. The other thing that's actually a bit unexpected use is from a company called IKEA, and I guess you know who IKEA is. So every year, IKEA has to publish a catalog with thousands of images of everything that you can find in their stores. And this year, the catalog for this year, from 60 to 75% of all the images that you see are not real. They're rendered. And they're rendered with our software. They do images like this. And why they prefer to do them with software and computers, because when they put an image in their catalog, it has to include only only products that you can find in an IKEA store in the particular country where the catalog is published. So if you do an image for Europe, you will have one set of things inside your kitchen. If you do an image for IKEA catalog in the US, it'll be slightly different because you have different kinds of things that you sell. So the way they used to do it before is they would actually build the whole physical model. They had a whole huge building where they build stuff, take a few pictures, tear it down, and then rebuild it again for the next photo shoot. This was very expensive, so they decided to try and do as much of that as possible with computers, and it's worked pretty well. Nobody really noticed that the images are not real anymore, which means that, yeah, we are getting close to simulating the actual real thing. And today my presentation will be in two larger parts. The first part will cover some of the theory behind the rendering equation and what we are trying to use as mathematics when we write our software. The second large part is focused on parallel calculations because rendering these images is not the fastest thing on earth. We have to find ways to make it as parallel as possible using multiple CPUs, multiple machines, GPUs, also cloud rendering, and all these interesting approaches to making things go faster. The other product that we are working on is called Phoenix FD. It's a fluid simulation engine. It can be used for simulating effects like fire, smoke, and also liquids. And my colleagues, Ivaylo and Svetlin, are going to talk a little bit about how we do that in the afternoon. And the other presentation that you will see in the afternoon is by Hristo Lessev. He will talk about general framework that he came up with for making a photorealistic renderer that's fairly extensible and configurable. That's right. Okay. So I showed you some of the results that we produced with V-Ray. It's based exclusively on ray tracing. It basically tries to simulate the way light rays bounce inside a scene. We can do both very accurate simulations, but we can also do some compromises because sometimes people just need to get an image out to see what the result would look like roughly. So this is controllable. You can either get a fast image and a fast approximation, or you can get a very detailed image that will unfortunately probably take a while to calculate. V-Ray is used for many things. I mentioned film VFX. It's used for TV commercials, product visualizations, architectural visualizations, and maybe at the end, if we have a little bit of time, I can show you some short clips of animations that we've done with V-Ray. Okay, so starting back with the first version of the rendering equation, this is the basic equation that all physically based renderers that exist today try to solve in one way or another. This was introduced in 1986 by a guy called James Kagia at SIGGRAPH paper. Basically, he summarized everything that renderers are trying to do in this integral equation, which assumes geometric optics. It doesn't take into account effects of light rays bending or diffracting. So it simplifies things a little bit, but it's enough to get most of the real-world light effects and simulate them properly. Originally, he wrote the equation for surfaces only, for hard surfaces, but it's fairly easy to extend it to do volumes in participating media, like we have done with Phoenix. It can also simulate subsurface scattering for things that have a semi-translucent appearance, like marble or wax or anything that's not really hard, but you can see a little bit into it. The rendering equation is basically a recursive equation because it tells you how light is transported from one point to another So there is, if you imagine that there is a, can you see the mouse here? Yeah. So we have a light emitting surface here, maybe, and it sends energy into the scene. This energy bounces off another surface and reaches potentially maybe our camera or another surface so that it can go on and bounce around. Kajia also proposed a solution to this rendering equation, which he called path tracing. The way it works is basically, in the real world, it's the light sources that emit energy and our eyes that detect this energy. But for the purposes of computer simulations, because the light sources are fairly large, but the camera is really small, so if we do the actual physical thing and start tracing photons from the light source and hope that they will somehow end up in the camera, this is very inefficient. It works, it can be done, but it's just very slow to get a usable image out of that. So the way things work with path tracing is you start the other way. You start tracing rays from the camera into the scene and try to find ways for those rays to reach the light sources. And the simplest algorithm that Kajia came up with is we just trace random rays from the camera. We reflect them off of each surface recursively until they reach a light source, at which point we just take the intensity of the light source and add it to the final image. This works, and it gives an image like this. Basically, for each pixel of the final image, we trace a ray into the scene, let it bounce around this scene until it finds the light source. This particular image didn't take too long. It was maybe a couple of minutes on my laptop. But if you want to get a usable result with no noise at all, you have to wait a long, long time. Back when Kajia wrote his paper, this time was even longer. So it was not really a practical solution. But still, it's a useful technique, and it can actually be extended a little bit so that you can get a lot better results, even with just slight modifications. One of these modifications is instead of tracing the rays randomly from each surface, you can figure out which is the most likely direction for the light to come from for this surface. Because if you have a mirror, obviously the light reflects from the mirror exactly at the angle at which it falls on it. So you can figure out the correct direction for tracing new rays from a mirror. From a diffuse surface, things are you just randomly trace rays in all directions, and there are all kinds of surfaces in between the mirror and the diffuse surface that focus lights in different ways. But you can do important sampling and figure out good directions for tracing those new rays. And the other thing that you can do is you can trace shadow rays directly from the camera. So from each point in our path that we had before, you can ask the question, is this point illuminated directly by any of the light sources in the scene? Because we know in advance what the light sources are, we can figure out what shadow rays to trace. So we can make the whole process a bit more efficient. So instead of waiting for any ray to randomly find the light, we can sort of guide the rays towards the light sources. And this works, and it gives us a slightly better image. There's a lot less noise compared to this one. Eventually, they both converge to the same thing, but one of them is computed a lot faster for the same quality. It's still not perfect. There's still a lot of noise because the light reflects here from this mirror and produces this caustic effect, which is actually one of the hardest things to do with the methods that we have for solving the rendering equation right now. The path tracing is an unbiased method for computing the image. It means that given enough time, it will get to the correct solution. You will not get any, it will basically be the final correct result. However, if we want to make the whole thing a lot faster, but maybe a bit less precise, we can add a little bit of bias to this, like a little bit of interpolation, and try to reuse information from one part of the scene to calculate the lighting from two other parts. The way this works, we came up with this method called light cache, which is a two-pass method. It basically does a first pass on the image called the light cache phase. Actually, let me show you how that works so that you can roughly get an idea. This is a program, it's called 3D Studio Max, that allows you to import 3D models and assign properties to them so that basically set up your scene so that you can render it afterwards. So the rendering goes through two phases. One is a light cache phase, and the other one is the final render phase. During the light cache phase, we trace a few rays around the scene. Remember what the illumination was at different points along the different paths. And in the second pass, we just interpolate those points. This short diagram of how that works. So initially, we trace rays from the camera. They bounce around. We remember these positions in a 3D structure in a point cloud that we can use in the second pass to interpolate the illumination. If we just use the light cache, this will be the result that we will get. It is sort of like the path traced solution, but it's blurrier. You can see these blotches. So there's no noise, but it's not a nice image. So we can combine the two things. We can combine path tracing with the light cache, and we can get a more accurate result. So for the first diffuse bounce, if we start our rays from the camera, so for the first hits, we use path tracing, so we trace new rays into the scene. And for the secondary bounces, we use this point cloud structure that we built the first time. And we get the final result, which is super nice. It's better than the pure path tracing. So again, if we compare it to the previous image, which was done only with path tracing and direct illumination, the one with the light cache has a lot less noise, so it's a lot more pleasant image to look at, but we still have noise in the caustic effects here. This is because the light cache only works for diffuse global illumination. It does not really handle light reflecting off of specular surfaces. But luckily for us, for many, many everyday scenes, caustic effects are not really, they're really subtle and not too important to the final result. So we can usually skip them, and in this case, the noise will just not be there. But anyway, caustics are a real-world effect, and we can, in some cases, we can ignore them, but in others, we really need to simulate them. And there are other methods, except path tracing, that are better suited to this approach. One of the first methods that allowed for the efficient calculation of caustic effects is called photon mapping, and it was introduced by a guy called Jensen in 1995. It's also a two-pass method. We have a preparation phase and the final render phase. And in the preparation phase, we trace rays from the lights. And I mentioned that this is a slow operation, and it is slow if we want those rays to reach eventually the camera, but that's not exactly what he does. He still traces the rays from the lights, but he just remembers the hit points of those rays in the scene. So every time a ray from a photon from the light source hits something in the scene, it is stored in a 3D structure called a photon map. And the precision of our solution depends on how many photons we trace. The more photons we have, the more precise solution we get in the end. Then there is a second pass, which is sort of like path tracing again. So for the primary diffuse bounces, we can use just regular path tracing, but we can use the photon map in all other cases. Here is an image where I just use the photon map. And you can see that the caustic effect here is really nice and smooth. I don't have any noise here. The image itself is a little bit noisy. It has these splotches. They will go away if enough photons are shot from the light source. Unfortunately, this takes time and it takes memory because we have to keep all these hit points in the memory all at the same time. So this can get very expensive. And there is an extension to photon mapping that deals with this problem. And I will mention it later on. But a good solution is to just replace the first bounce with regular path tracing like we did before. So this is kind of what we get in the end by combining photon map and path tracing. So it's a good image. And for a long time, this was probably the best method to calculate illumination, especially in interior scenes. It's very accurate, but it has a few drawbacks. First of all, the number of photons that we need to trace from the lights might be difficult to determine in advance. So we don't know how many photons will be good enough for a given scene. We may need many, many photons to get clean caustic effects. In this image, you can still see that there is a little bit of splotchiness here. And it can be removed by tracing more photons, but this is expensive both as render time and memory. Also, things become difficult if we have a light source that is very far away from the parts of the scene that we're actually interested in. So if you try to simulate something like the sun illuminating the earth, you can trace photons from the surface of the sun, but most of them will never get anywhere. So a lot of computation can be wasted in this case. And it's difficult for photons to handle very large light sources. Like it's difficult to use them in an exterior scene where you have sunlight and skylight because the photons have to cover a very large area. They work very well for a closed space, like this auditorium would be a perfect example for using photon maps, but they will not work if you want to render a landscape. However, for a long time, there was no better way to do it. And then in 1998, a guy called Eric Veach published his master thesis on light transport simulation. And he introduced another version of the rendering equation called path integral formulation, which I'm going to explain a little bit right now. So the rendering equation defines how light bounces off of one surface. So it's basically just a local equation that we can repeat a number of times to get a path, a light path with with a given length. So let me give you an example with my first slide. So in this case, we have a path with just, so you count every endpoint for every ray. So in this case, we have a path with 1, 2, 3, 4, 5 vertices. But in a normal scene, there are paths with all kinds of lengths. So he decided to classify them and to group them in all the paths of a given length are grouped into a function called a measurement contribution function. It can be expanded, and you can get the exact formula for what this function looks like. But the point is that if you take an integral over all the possible paths of a given length, and then you take the sum of all the paths with all different lengths from 0 to infinity, you get a version of the rendering equation here that is defined over, not over the surfaces of the scene, but is defined over all the possible ways paths can be generated from the camera to the light source. And when it's formulated in this way, the rendering equation can be solved with a Monte Carlo method, the general form of which is, I'm sure you probably know this very well. You take the the average, you take a number of samples, and here by sample we mean different paths in the scene from the light sources to the camera. We divide each of these, the contribution of each of these paths by the probability with which the path was generated, and we just take the average sum of all these different paths, and we get a solution to our equation. This means that we can generate paths from the camera to the light sources in any way that we want, so long that we can compute their probabilities. So in path tracing, we start from the camera and we bounce rays around the scene. With the photon map, we start from the lights and we trace rays towards the surfaces. But we can do anything else. If we wanted to, we can start from any surface and try to find ways to get to the camera and to the light source. And we can solve the rendering equation in any way that we want. Related to that, in another paper, we also introduced another concept, which is going to be useful in this context. And it's called multiple importance sampling. His idea, basically, he had an observation that if we have a function that we need to integrate, and here is just a very simple function showing that I can't really draw anything in OpenOffice with curves. But it basically shows you that the function has two areas that are maybe interesting for us that contribute a lot to the result. And maybe we have one way to generate samples that approximate the function very well in this area. And maybe we have another way to generate samples that approximate the function well in this area. So, but each of those techniques only works for its own part of the domain. So Vich realized that there is a way to combine those two ways of sampling the same function, and he called it multiple importance sampling. Basically, you can, if you have the same function that you have to integrate and you can sample it, different parts of it with different distributions well enough, you can combine all of these into one estimated integral that's provably optimal. There's a lot of mathematics involved. But let me give you an example for that, and which we use in V-Ray actually to calculate direct lighting. Direct lighting happens when a light source emits a photon. That photon hits a surface and it bounces directly into the camera. So there's only one light bounce. It's called direct lighting because it does not involve any other. It just involves one light, one surface, and the camera. There are two general ways to sample the direct illumination. One way to sample it if we start from the camera, because in V-Ray, like I mentioned, we usually start tracing from the camera. So we trace a ray into the scene, it hits some point, and then we have a choice of two techniques to find the light source. One of these techniques is to randomly trace reflection rays from the surface and hope that maybe some of those rays will hit the light source. And the other thing that we can do is if we know where exactly the light source is in advance, we can trace rays directly to it and figure out if anything else is blocking those rays. Because if we had an object here that is blocking the light, we will have to find how much of the light is blocked. So that's where we need to trace the shadow rays. But these are two techniques that calculate the same thing. One way is better in some situations, the other is good at other situations. And here is an example that I rendered with V-Ray. We have a few spherical light sources, and we have 4 strips of materials with different properties. The material that is closest to the camera is very mirror-like, and materials further from the camera here are more diffuse. So we can see that if we sample only the light source, so if we just trace shadow rays toward the lights, This works well for the relatively diffuse surfaces, but it produces a very noisy result here if we have a very mirror-like surface. And this is normal because the probability that one of these shadow rays will exactly match the reflection direction relative to the camera is very, very low. So, and the result is this noise that we get. It will eventually clear up if we trace enough samples, but it's just very slow. If we do the other thing, if we just trace rays close to the reflection direction and try to find the light sources, we get almost the reverse. We have good results here for the perfect reflection, but we have a lot of noise here in the very glossy surfaces, because in that case, the reflection rays here are spread over a very large area, and only some of them will hit the light source. So that's why we get a lot of noise here. But if we combine both techniques with multiple importance sampling, we get the result that is good everywhere. And we didn't do anything more special than combining these two images with appropriate weights. Here you can see what the weights are. This is just the reflection component, and this is just the specular component. And when we add those together, we get the final result. And each gives all the formulas for calculating the proper weights for these things. How can this be applied to the whole of the rendering equation? Obviously, we have to simulate more light bounces. We don't only have direct illumination in the scene. Vich proposed a technique that is called bidirectional path tracing. And it involves tracing rays not only from the camera or only from the lights, but you do both of them. You trace one camera ray and you trace one ray from the light. And then you connect the endpoints of those paths with a shadow ray. So it's sort of like a generalization of both of direct illumination, but instead of doing it with just one surface in between, you have more surfaces. But that means that you can get the same path in many different ways. So if we consider this path here, we can generate the same path either starting from the camera and bouncing off the surface until we reach the light. It can be done in reverse. You can start from the light source and bounce around until you get to the camera, or you can do any combination in between. So you have different techniques to calculate the same path. And these techniques can be combined together with multiple importance sampling. It's a little bit tricky to get all the probabilities right, but it is doable, and you get, if you do everything properly, you get a very good result. This image is calculated with bidirectional path tracing, and you can see that it's almost perfect. The caustics are nice. The diffuse illumination is very good. It's also an unbiased method. There is no any interpolation going on or density estimation. You still get the correct result. The only downside is that you get this noise here in the reflections. And this happens because the bidirectional path tracing does not have a very good way to generate paths that make caustics visible through a mirror or caustics visible through glass. Very easy to ray trace. Why is that? Because the probability that a ray from the light source will just bounce in the right way is very, very low. And the more mirror-like the surface becomes, the more difficult these indirect caustics are to simulate, and you get more noise here. Thank you. You can also, in the same framework, you can incorporate any other path generation strategy. So if you are interested in a particular part of the scene, you can start from that point. You can generate rays towards the camera and towards the light, and you can incorporate that into the whole path tracing framework, and it works really well. So the only thing that it didn't do well, like I showed you, is the caustics seen in a mirror. The photon map, on the other hand, handles this effect. If we go back to the photon mapped image, just find it. You can see that the caustics here were okay. We didn't have any noise. So the question is whether there is a way to incorporate the photon mapping technique into the whole bidirectional path tracing framework. And the answer is yes, actually. But before that, there is a technique, there is an improvement to photon mapping called progressive photon mapping that was introduced by Jensen. Again, he's the original person who introduced photon mapping. And he basically showed a method to accumulate not an infinite, but an ever-increasing number of photons with more and more precision. For this purpose, he proposed the progressive rendering algorithm, which goes in several passes through the image. And at each pass, more photons are traced and more photons are added to the result. But at the same time, the radius where we look for photons is reduced so that we can get a more accurate estimate of the result. So it sort of works like this. We trace a number of photons. We start with a relatively large radius. And at each pass, we reduce this radius by some proportion. We resample the previous passes to fit the new decreased radius, and then we combine the photons from the old passes with the photons of the new passes, and we get the final, more accurate estimate. This works well, but it's still photon mapping. So if you want to render an open scene like a landscape, it's still difficult to do it. But it's possible to combine bidirectional path tracing with photon mapping, which was done in 2012 by several people at the same time, actually, one of them also a Bulgarian. It reformulates photon mapping in the same path integral version of the rendering equation so that it can be added just as another way to generate, as another technique to generate paths from the camera to the lights. And it's actually one of the most accurate and robust algorithms that exist today. The only tricky thing is that it's difficult to implement it correctly. There's all these probabilities are difficult to get right. So it just adds photon mapping as another way to connect paths from the light source to the camera. And this is an image that is rendered with Vertex connection merging, which is the way this combined way to compute things was called. And it seems to be the perfect image. It's got the caustics are all right. There's no noise in the mirror, and given enough samples and enough time, eventually it will converge to the correct result in the final image. Things get a little more interesting and more complicated when you get to participating media like fog, clouds, and so on. You can still use those same techniques, bidirectional path tracing, photon mapping, and vertex connection and merging. But there is also another extension of photon mapping for volumes specifically. It's called beam tracing, where instead of storing points, photon hits, you treat the whole path of a photon as one line, as one beam, and then you can keep those beams in a similar structure to the photon map, and you can use it to estimate the irradiance at various points in the volume. And this can be incorporated in the same path integral version of the rendering equation. This was done this year at SIGGRAPH. There is a paper that describes how to do that. It's incredibly tricky to get it right, but it's a very good method to simulate effects like subsurface scattering, volumes, and all kinds of things. So this is currently the best way possible to render anything. So this is for the first part of my talk. Do you have any questions about these things? Yep.
Couple of things. Do you have timings for the pictures that you showed us?
They all took approximately the same amount of time, which was about 2 minutes.
Okay, what's the perfect case? If you did the complete ray tracing, what's the
how long it would take to compute it? On my laptop, because all the rendering was done on my laptop, it would take maybe 10 minutes or so.
And what was the others?
Hmm?
What are the others?
Well, it depends on what you want to get as a final result, right? You can leave because the vertex merging, the bidirectional path tracing works in a progressive way, which actually let me show you how that works. You define yourself when the image is done.
Yeah, but the question is, a human cannot differentiate it from a generated image anymore.
I'm sorry?
A human cannot differentiate between the real image and the simulated image.
Well,
when do we get there? How long does it take?
Hours. It can take hours. Especially, this is really simple scene, right? So this is basically how the bidirectional path tracer works. It just goes through the whole image in passes. Each pass makes the image slightly better. But if you want to get a perfectly noiseless image, this can easily take hours, especially for a more complex scene. And this is what I'm going to talk about in the next part of the talk. I'll talk about distributed rendering and how we can use multiple machines to do the same thing faster.
Yeah, I have one or two questions.
Yes.
So if I understand correctly, for each ray you are taking into account all the physics in the materials, reflection and diffraction and all these things, right?
Yep.
Now, I see an inflationary process with your system in the sense that if you have from basic ray, you have a shadow rays, then depending on the number of surface, and that's my next question, that's an exponential behavior.
The rays don't really increase exponentially because you can use things like Russian roulette to probabilistically choose what you want to do.
Yeah, yeah.
So it's not that bad.
This is related to my next question. So in all the pictures you have shown this one, the IKEA kitchen and so on, so you have, say, a few tens or hundreds of surfaces.
Yes.
Now, in a realistic picture, you may have zillions of surfaces to take into account.
Yeah.
So how is your system evolving? Because I see exponentials everywhere.
Well, for the ray intersection, for the intersection of rays with the surfaces, how fast this will be depends on what kind of, you can use acceleration structures to make the whole thing. You don't have to trace to check every ray against every surface. You can build something like a bounding volume hierarchy. You can build a KD tree on top of that. So to intersect the ray with all the surfaces in the scene, you don't really need that many calculations if you do your acceleration structure right. And we have had clients who have really large scenes. They have millions of triangles. In the recent case, they had to render a model of a whole cathedral scanned with laser, which was something like 600 million triangles. And it renders in a realistic time. Like his scene rendered in maybe 15 minutes per frame because he had to do an animation. So it wasn't so bad. The render time doesn't increase linearly with the number of triangles. It's better than that.
Can I ask you another quick one?
Yep.
I see that you're using blocks, but then at the right-hand side of the blocks and the bottom half, the block sizes change.
Yes, I will talk about this. Yep.
So I'm wondering what kind of important sampling technique you're actually using to sample from the paths. Is this something like Metropolis or is it
we don't use Metropolis light sampling for several reasons. First is that Metropolis is useful when you have a really difficult lighting situation because it can find the important paths and focus there. But if you imagine a case that happens more often than not, if you have an environment scene where the lighting doesn't come from any particular direction too strongly, if for this case where it's not a difficult scene, it's just an everyday scene that happens all the time, Metropolis actually performs worse than just regular path tracing. And this is because with path tracing, you can do things like stratified sampling. You can use jitter. You can reorder your samples in a way that ensures good convergence, while with Metropolis transport, you have to use perfectly random numbers, which actually produces worse result.
Okay.
So we've done those tests, and Metropolis does help in that classic scene where you have a light in a corridor and the door between them, and it's perfect for that case, but for everyday scenes, it's worse. So we just use regular bidirectional path tracing. Yep.
How do you consider the interaction inside the volumes and not only on the surface?
For the volumes, I don't know if you will mention this in the afternoon, but we'll talk about shading the volumes a little bit in the second talk in the afternoon. There are different ways to do it. One of the simplest ways is to choose a random point inside the volume based on the density. If you have a ray of light going through the volume, you choose just one point probabilistically, and you treat that point as a small light source. So, if you average a lot of these light sources, you get the correct result. So this is one of the easiest way to do it. But you can also do other things. You can do ray marching, and at regular intervals, you can evaluate the lighting in the volume. And this also works very well. Unfortunately, of course, for volumes, things are just slower because you have more calculations. But it's doable and it works. We haven't implemented the beam tracing version for illumination inside volume, so we just use regular path sampling. But it still works. Okay, yes.
If you have multiple light sources in a scene of different brightness and intensity, how does that affect the tracing?
This can be handled in several different ways. For the moment, the way V-Ray is coded, we treat each light. So at each hit point, we evaluate all the light sources. Obviously, if you have a lot of light sources, this gets very slow. So we implemented a system where V-Ray would choose out of all the possibly thousands of light sources in the scene, it will choose just a small number, maybe 10 or 16 light sources based on an estimate of their contribution to the shading point that we are processing right now. So it will probably choose a few lights that are close to that point with an algorithm similar to Russian roulette. So in the end, it converges to the final result. And it's still pretty fast. Okay.
I propose you to take more questions to the end. Otherwise, we don't
have time.
We have a second part still to go.
Okay.
Is it okay? Is it short? Try. Okay.
About the colors, how do you handle the colors? Because you always talk about the photon, but if you send a white light, it should be changing colors.
Yes. Okay. So for we usually pick 3 wavelengths, which are red, green, and blue, and we solve the render equation for just those 3 wavelengths. So for the photons, each photon has information about the energy at those 3 wavelengths, and then it interacts with the materials in the scene at just considering those specific wavelengths. It's a bit difficult when we have to simulate effects like dispersion, where you can break a white ray of light into a spectrum. This is also doable, but then you can't use RGB colors anymore. So we just pick a wavelength randomly, and we calculate the rendering equation just for that wavelength, and then we combine all the results together. There are other renderers that work not with 3 wavelengths, but with more, like 7 or 10 or more. And you get more accurate light interactions. But the basic principle is still the same. Okay, so the third part of my talk will be about parallel calculations on a single machine using multithreading, and also across many computers using distributed calculations. And I will also talk about using specialized hardware like general purpose GPUs. I'm not really going to talk about the Xeon Phi. It's just something that I want to mention as a possibility there. The Xeon Phi is a card from Intel that has 240 processor cores that can work in parallel. It can be very fast for some things, but we found that it's not really, it still has ways to go to be really useful. So I'm going to talk about the CPUs and GPUs. So an image can take a really nice image can take a long time to render, anywhere from hours to some extreme cases, days. We've had clients that had to render images that are really large, like 40,000 by 40,000 pixels or something like this. Well, they're large for us, maybe. You have a different idea of large problems, but anyway, the question is that you have to do this in the fastest way possible. In order to do any kind of task in a parallel way, we have to find a way to split the problem into independent chunks that we can calculate in parallel. Then we have to collect all the computed chunks together to get the final result. And a few words about multicore CPUs. They're very common today. Like when we started 10 years ago, it was very rare to find a machine with 2 CPUs. Most machines were 1 single CPU. And it was a bit unfortunate because there is a lot of code in the internet that's not really designed with multi-threading in mind. So sometimes we have problems if we have to use third-party libraries that were written a long time ago. Nobody really thought that they would be running on 38, 48 cores. So it's a problem. The other thing that comes up with multithreading is that we assume that within a single machine, all the different processing units have equal access to all of the RAM. This is a basic assumption that we did in V-Ray a long time ago, simply because that's the way machines worked back then. Today, there are machines with different architectures, non-uniform memory access, where different CPUs access different parts of the memory. And I will mention this briefly, but it has advantages and disadvantages. Multi-threaded programming is widely available right now. There are low-level services that are provided by each operating system, but there are also higher-level libraries that can be used, like OpenMP. I think all the modern compilers support OpenMP, so writing multi-threaded code is really easy. There is also Intel Thread Building Blocks, which is a free library from Intel, and it's very well designed for all kinds of parallel calculations. We don't use any of these, unfortunately. Back when we started, they were not available, so we had to deal with the low-level stuff that we get from the operating system. But if you do things today, you have a lot of options. So everything is fine if you do things in parallel with multiple threads, but there are a few issues with access to the system RAM. If all the different cores of the processor try to access different parts of the data set, because all the CPUs have to go through the same system bus, things can get really slow. Also, if there is any kind of sequential code, and sometimes there is, not everything can be made parallel, this can slow things down. And if the CPU, if one of the CPUs has to wait for something, for example, it needs a certain piece of data from the main memory, it can't really do anything in the meantime. Hyper-threading on Intel CPUs avoids this problem to some extent, but it's something that needs to be kept in mind. So this is the architecture that we normally assume in V-Ray. We have different CPUs. They have a different number of cores in them. And all CPUs are connected to the system RAM through a single bus, and they all have access to all of the memory all of the time. The problem with this approach here is that the connection to the system RAM is a bottleneck. It works for 2 CPUs, but when you put 4 CPUs or more, things get very slow. So that's why hardware vendors like Intel and AMD introduced NUMA, which stands for Non-Uniform Memory Access. And it basically gives each CPU a dedicated piece of the system memory, which it can access very quickly. But if it needs to access any other part of the system RAM, it has to talk to one of the other CPUs and ask it for that data. And unfortunately for us, this architecture doesn't work well for rendering because we have really large data sets that can be many gigabytes of memory. And it's not possible for each of these separate blocks of memory to hold all of the data sets. So the communication between the different processors, trying to get different pieces of the data from each other becomes very slow. So if V-Ray has to run on a NUMA machine, we just tell people to run several copies of the application, and each copy runs on its own core, trying not to share any information with all the other NUMA nodes. Here I talk a little bit about sequential parts of the code. Our rendering process goes through several phases. There is an initial setup phase, then there is a rendering phase, which could be, for example, photon tracing, which can be made highly parallel. But then there is perhaps another sequential part, which would be, for example, building a 3D structure out of the photon hits to make a photon map. Then there is perhaps another rendering phase, which could be the final rendering, which can be done in parallel. And then we write the final result. But there is something called Amdahl's law, and it basically says that if you keep adding more and more cores to a system, so you can make these parts as parallel as you like, but even if they vanish completely, you still have the sequential parts, and they will be a bottleneck for the whole application. And it becomes difficult to find parallel ways to do. It can be difficult to do these things in parallel. So we can't scale up to too many cores without issues. So here I talk about how we split the work for an image and give it to several processors. For rendering a final image, it's very easy. We just split the whole image in little squares, which are each square is calculated by another CPU thread. And you saw this a bit earlier. There is a bit of a problem with this because some parts of the image may be more difficult to calculate than others. And it used to happen very often that all of the image is complete, but there is one thread stuck doing something in one bucket somewhere in the middle of the image, and all the other CPU cores are just standing idle waiting for this one to complete. So that's why we added this dynamic bucket splitting thing. So when V-Ray gets closer and closer to the end of the image, it reduces the size of those buckets so that it can make better use of the CPU cores. When you have to do photon tracing, the things are a bit easier. Because we know in advance how many photons we want to trace, we can just divide them in equal chunks and give them to a separate computing thread. And in the end, just take all the photons and build one photon map. So that's it about multi-threaded rendering. The other thing that we want to do is use not just one machine for rendering, but use several machines to work on the same image. And this has its own set of issues. One of them is that we have to first transfer all the data to all the machines. We have to also give them chunks of data to compute. We have to get the results back. And occasionally we may need to do some kind of synchronization between the machines if they need to share some kind of intermediate calculations. The architecture of V-Ray right now is client-server. We have one machine, which is usually the workstation where the user opens the scene and assigns materials, lights, and so on, and starts the rendering process. And then we have a lot of other machines called render servers, which do the actual work. So the client machine has to transfer the input data to each render server. It has to give them work to do, and it has to collect back the final result. For path tracing, this is very easy to do. You send bucket regions to each render server, you get pixels back, and you write them into the final image. But for things like vertex connection merging, things are more complicated because you have also a photon tracing phase. You have a photon map that at each pass has to be given to all the render servers. And the whole process goes something like this. So when we start with the vertex connection merging rendering, we start initially with pass through the image without having any photons. So we just give little squares to all the little render servers to calculate. And each render server calculates a region for the final image, and it also calculates a number of photon hits from the light sources, which are collected in a photon map. So at the next step, we have to take this photon map and send it back to all the other render servers. And then we move to the next pass, where each server uses the photon map that was computed at the previous step to compute buckets for the next step. So there's a lot of data going between the machines. And unfortunately for us, this is a bottleneck, which we didn't anticipate, because when we designed the original client-server architecture, we did not have the vertex connection merging, so we did not realize it's going to be a problem. But there it is. So it's something that we need to work on. We haven't solved that part yet. But you still get quite a good speed up if you use multiple machines. The communication is a bit of a bottleneck, but if you have a heavy scene that requires a lot of calculations anyway, the network communication that happens here all the time is usually not that big anyway. A few words about GPUs. They are a very different architecture from CPUs. They are massively parallel. On the CPU, we have anywhere from 8 to 64 threads running at the same time performing work. But GPUs usually have many thousands of threads running at the same time. So they can be very, very fast, especially for things like path tracing, which are very easy to do in parallel. How do they do this? There are a few reasons why GPUs are so good at multi-threading. First is that they have a SIMD architecture. They can do the same operation on several pieces of data at the same time. Here I'm mostly talking about NVIDIA GPUs, which currently operate on 32 pieces of data at the same time. So they can be adding 32 numbers together or dividing 32 numbers in parallel all at the same time. They also don't have the concept of context switching. On the CPU, when you have to move from one thread to another, there's a lot of work that the operating system has to do. It has to save all the CPU registers somewhere in memory. It has to load the registers for the thread that's going to be executed next. It has to update, if the thread is from a different process, it has to update virtual address tables and whatnot. So threads on the CPU are very, very heavy. The GPU doesn't have this problem. Each thread basically has a bit of it has resources allocated to it which are not used for anything else. So the GPU can switch between threads very, very quickly. And it also has automatic thread scaling. If the GPU needs to wait for an operation to complete, for example, if it has to load something from memory and it's not in the cache and has to go to the GPU memory to fetch that data, if this happens on the CPU really has nothing else to do in the meantime. It just has to sit and wait for the data to come from the main memory. But the GPU is not like that. If something like this happens, the GPU can try and find another instruction that it can execute at that time. So it can do a lot more. It hides the latency of the main memory very effectively. There are, of course, it's all very well, but it has its own problems. And one of these problems is that because of the SIMD architecture, if different threads have to execute different code, this becomes slower. The other thing is that because you have thousands of threads, if you need to do any kind of synchronization, it's really expensive. And the other thing that happens is that if you have complex GPU code, it's not currently handled very well. As your program gets more and more complicated, it tends to run slower on the GPU. It's just something that we found out a bit later in our development. There are two ways to program for general purpose GPUs today, OpenCL and CUDA. OpenCL is a standard that was developed together with several companies. And it's supposed to be device independent. You can write an OpenCL program and it can run on any device that supports OpenCL. Unfortunately, right now, that's a bit of a wishful thinking. But it's there. And it's the only way to program for some GPUs, like AMD GPUs currently only support OpenCL. The other widely used solution is CUDA, which actually works pretty well, but it's locked to a single vendor. It's only available on NVIDIA GPUs. They're both not too dissimilar from each other. Both describe a C-like language for programming the GPU. But CUDA is probably a bit more user-friendly, and it's a bit easier to take an existing application and port it to the GPU if you use CUDA. With OpenCL, you have to do a lot of extra coding. Also, it's for both of them, both OpenCL and CUDA, it's still difficult to debug your application. So if something goes wrong and your GPU code crashes, it can be very difficult to figure out what exactly is wrong. So we have a GPU version of V-Ray. It can do path tracing on the GPU. And it's trivially parallel. We just calculate each pixel in its own GPU thread. We had a few problems doing this efficiently. 3 problems, actually. One is to keep the GPU busy, because the GPU is not like the CPU where you give it a program and it can run for hours on end doing that. It doesn't work like that. You have to give it small pieces to calculate, and you have to give it some chunk of data to work on, and then you have to read the result back. So doing this efficiently on the GPU and maximizing the utilization is a bit tricky. The other thing I mentioned is code complexity. As we added more and more GPU code, things started to become slower, and we had to figure out ways around that. And the other thing that I also mentioned is divergence in the code. If the different threads have to execute 2 instructions that are too different, the efficiency of the GPU falls. So you need to be careful about that. So to keep the GPU busy, if you do things in a naive way and you prepare the data on the CPU, you give it to the GPU and read back the results, you get something like this, where the GPU only works some of the time. And we found that we can actually use multi-threading to improve this. We can have many different CPU threads preparing data for the GPU. And even though we have only one GPU, we can arrange things in such a way that the GPU is always busy. It always has something to do. So while the GPU is working on something, another CPU thread can be working to prepare the next piece of data to give to the GPU. And this has helped to maximize the utilization quite a bit. For the code complexity, we had to do something that's very hacky. We had to basically find ways to recompile our GPU code depending on the input data. So when we have a scene to calculate on the GPU, we analyze that, we figure out what features are needed. For example, what kinds of light sources are in the scene, what kinds of materials are there, and we delete portions of the code that are not relevant for that scene. For example, we have a lot of code dedicated to calculating motion blur on the GPU, but a lot of scenes don't really have motion blur, so we can just delete this code for those scenes and get the whole thing to run a little bit faster. For the code divergence, the problem that we had is that even though you can have pixels that are next to each other in the final image, once the rays start bouncing around the scene, they can hit different objects, they can have different materials, and ultimately they may need to do different things, and it slows the GPU down a little bit. So we found out that because all these random walks through a scene, they're not really random, they're pseudo-random, so eventually they depend on a single seed for the random generator. If we give pixels that are next to each other the same random seed, we can get the rays to bounce in approximately the same way. And this improves the coherency of the code on the GPU. So it makes the whole thing run 20–30% faster. And here I actually did a few versions of the same image, which are rendered in just a slightly different way. In this scene, the image was divided in pixels that are 32 by 32 pixels. The pixels in each block are traced line by line. So if things are perfect, each line of 32 pixels is calculated by one warp, by one GPU processor. And here I'm just giving different random seeds to the different pixels in each block. For this image, I gave the same random seeds to all pixels in each block. And you can probably see that you get little square artifacts here and there. And they go away if you leave the whole thing to calculate for long enough. But the render time for this was 3 minutes and 30 seconds. The next thing that I did is give the same random seed to each line of pixels. And you can probably see the horizontal artifacts here. And they will disappear if I give enough time to this as well. But for this image, I calculated the exact same number of samples, but you can see that the render time is longer. And here I did the same thing, but instead of giving each line the same random seed, I give the same seed for each column. And even though these two images basically do the same thing, one of them is slower than the other. Why is that? Because when you give the same seed for every column, you get different threads in a single warp to go in. There's a lot of divergence in one single line. So the GPU has to do a lot of dissimilar things for every thread in a single warp. And this is with each pixel having just a completely different seed from all the others. So this was 6 minutes. And if you compare all the images, they get you the same result, but you get it at very different render times. So one was almost twice as fast as the other. So that was actually a pretty neat thing that we found recently. And you can, so this was GPUs. You can put several GPUs in one machine. NVIDIA has these machines called VCAs, Visual Computing Devices, which have 8 GPUs. And you can connect these machines in a cluster they all have InfiniBand, so you can wire them together, very fast network connection. And you can use them to do distributed rendering across all these GPUs. And we actually did that because the distributed rendering system in V-Ray can utilize both multiple GPUs and multiple machines. And it worked pretty well. We used it to render a short animation project called Construct. The whole rendering took a week, maybe, on NVIDIA's cluster. But it would have taken, if we had to do it on CPUs, we calculated that it would have taken us something like maybe a year and a half to calculate it on regular CPUs. So that was pretty neat. And if I have this, I think I opened the Construct movie somewhere, and maybe I can play it to you. If it's still in the browser's cache. The sound is going to be from my laptop. I'm sorry for that. So yeah, that's what we use the whole cluster for, just rendering pretty images. But it was a cool test. All this was done on GPUs. All the calculations were performed on a GPU. All of that was path traced, and you see a small resolution version here, but we had to render this at a resolution that's something like 4K, and it had to be done in stereo, and it had to be done at 60 frames per second. So that's a lot of frames to calculate. And the GPUs helped us to do that. We wouldn't, like I said, if we did this on CPUs, it would have taken us a lot longer than that. And that's the end of the second part of my talk. Yeah, just a few words about cloud rendering. You know about the Amazon Elastic Cloud, you know about the Google Compute Engine, you know about Microsoft Azure. They basically allow you to rent thousands of machines and use them for whatever you like. In our case, we just use them for rendering. And we've done tests where we were able to use, well, it's easier if you do animations because you can calculate each frame of the animation on a separate machine, and frames are just trivially parallel. They don't depend on each other, so it's a bit easier than doing distributed rendering. And recently we used something like 10,000 nodes from the Google Cloud to compute an animation for a client. And it works pretty well. All right. Any questions?
Thank you very much first. And well, we proceed with questions until you feel like going for lunch. So you first, you said? Use the microphone, please.
Yes. So you mentioned the SIMD property on the GPU. I'm
Yes.
wondering whether you also explicitly vectorize your algorithms on a CPU.
No. We started.
Would that be feasible or possible?
We started recently looking into that, and there are pieces of the code where we can do parallel calculations on 4 numbers at the same time using 4 component vectors. and it does make things faster. For example, we use this when we had to optimize hair rendering. So it gave us maybe a 30% speed improvement, which was good. But we can't use it everywhere. But in some places, we can do that.
Yeah.
So I was just going to ask something similar. So what's your data structures? How do you pack? So for each photon, I guess, if you're making photon tracing, for example, you need to have 3 colors.
Photon tracing, for photon tracing is just a point cloud. It's a KD tree where you you build a binary tree of all the photons. So because we need to be able to do very quick nearest neighbor lookups in the photon map, so we build a binary tree out of that. And for each photon, we store the energy for each of the wavelengths. So it's a color. It's a 3-component color. We also store the hit point. Obviously, we need to know where the photon is. So that's one point. We also need to know the surface normal at the hit point. If only because we need to figure out if we hit the surface from the other side, we need to know whether the photons are on the same side of the surface or not. And I think that's all that. For the vertex connection merging, we also need to store the probability for the photon to get to that point.
Okay, so is it then structure of arrays or arrays of structures or independent?
For the photon map, it's
no, in general, not necessarily photon.
We do use structures of arrays at a few places in V-Ray, but usually, unless we have a reason to do it, it's just an array of structures. For the photon map, it's an array of structures.
Okay. I have one question out of being a layman. When you have this kind of edge effects, depending on how do you segment the image and how do you render it, does it need manual corrections, or is not touched after the computers have finished with them? I mean, does it need artistic touch after?
People usually do that, yes, for various reasons. Sometimes if you need to do slight adjustments, like increase the contrast a little bit, make the whole image a little bit brighter or darker, there's no need to re-render the whole thing. You can just change the final colors. So they do that. They do post corrections on the image. It's very rarely that you will see the raw render. So everything is usually, yep.
Excellent.
So you showed us several ways to either increase the speed and decrease the quality, or do the inverse. Yep. Now that's pretty complex because there are many dimensions. I'm wondering about yet another one. Do you do geometrical simplifications? Do you have a path where you simplify the geometry to speed up these?
We have thought about that. We experimented with converting geometry to voxels so that we can do a level of details when we have objects that are relatively far away from the camera. And we hope that we wouldn't have to ray trace against the entire geometry. The original motivation for this is for people who wanted to render landscapes because they have trees and grass and shrubs and everything, and when you multiply that for a whole forest, it's a lot of geometry. And this worked to some extent, but we had a few problems with that, and one of the problems was if you have a reflective object, how do you represent it with voxels so that it still looks like a nice reflective? If you have a sphere, for example, it's a glass sphere, how do you represent it as voxels and it still looks like a glass sphere? We couldn't figure out a good way to do that. So for the moment, if you want to do it, you have to manually make several versions of your geometry with the desired level of detail. And you can tell the render engine to load a different version of the object depending on how far it is from the camera, for example. But there's still manual work to prepare the geometry itself. We were looking recently at some mesh simplification algorithms, which seem actually quite promising, but we haven't implemented them in V-Ray yet.
Okay, thanks. Okay. Another question I had was, after you've done your ray tracing, you know, you can assign to different areas of the output image a certain confidence that you have done well enough in this area, right? Because you get a certain sampling rate. Do you do a softening, a post-processing of the image that takes that confidence per image area into account?
No, not right now. There's a little bit of filtering of the image, like a pixel filter. It slightly blurs, and it's mostly done for artistic purposes, because if you have very small details, they tend to flicker a lot if you don't filter them. But other than that, we don't really do anything.
Is there a reason for that? I'm really asking because for our background, whether this is something that we should be avoiding or whether that makes sense.
We haven't tried it, so I don't really.
Fair enough.
I don't really know.
Thanks.
Any more questions? No. René?
So do you think that your framework would be okay for the case where you have many rays with an infinity of wavelengths, and each material has a large quantity of processes to take into account?
It will work. It just depends how long you want to wait for it. But it will work. There is no the basic equation that we solve, the rendering equation, you can generalize it to do integration over all the possible wavelengths. So, and we've sort of done this when we had to do dispersion. So you get the light breaking into rainbow. So this is doable. It just takes more time.
And memory.
And memory. Yes, well, it's always like that. Okay.
Out of curiosity, how do you import new materials? How do you create materials? I mean, do you have to study a real material? What are the properties that you import?
There are different ways to do it. There is some research that was done in how to translate actual physical materials into sort of mathematical formulas that can be calculated. There are some BRDF models that approximate real materials well enough. And we use those in V-Ray. We have several different BRDF models. Blin, GGX was implemented recently. There's also a diffuse Lambertian model. But we also did our own research on how to scan actual materials. So you can take a piece of material, photograph how it looks from different angles and actually Ivaylo worked on that. And he can tell you more details if you're interested. But once you scan this material, you can then take it into V-Ray and render it, and it will look just like the real thing. And for some materials, it's really hard to do it any other way, because some materials have very interesting properties, like they can look blue from one direction, but yellow from the other. And there is no way you can mathematically describe that. So in this case, using scan data is the only way. And it seems to work pretty well. Okay, anything else?
Okay, so if there is nothing else, before we depart, remember that there is a second part of this session today at 2 o'clock, again here, with two shorter presentations. So thank you very much for coming this morning, and see you this afternoon, hopefully. Yes?
Thank you.